This is a continuation of our IB Physics Topic 7 notes. In this video, we'll briefly review decay, then we will look at nuclear fusion and fission. So, we've seen that certain nuclides, certain elements, are unstable, which means that they spontaneously change. They become a totally different element. We call this process decay, or when it happens spontaneously, it's natural transmutation. We studied three types. The first was alpha. That's when we have a nucleus that emits an alpha particle. So we start with some parent nucleus. In this case, we have radium-226. And alpha decay means 4 of the nucleons, 2 protons and 2 neutrons, are ejected from the nucleus. We call 2 protons and 2 neutrons an alpha particle. But it's the same as a helium nucleus. So helium, a nucleus of helium, has 2 protons and 2 neutrons. So once we eject this helium nucleus, this alpha particle, the number of protons has decreased by 2. So this has gone from 88 to 86. And because we now have 86 protons, we have a different element. We have radon. And the total number of nucleons in this nucleus has decreased by 4. So that goes from 226 to 222. Right, so we started with radium-226, and it spontaneously decayed, which means it shot off. It emitted an alpha particle, producing or leaving behind as the daughter nuclide a radon nucleus. Now, if we compare masses, right, the mass of this radium is actually bigger than the mass of helium here, plus this radon. And because mass and energy are equivalent, this means that the way we've written our equation here, we have more energy on the left than the right. So we need to add some energy to the right side in order for this to really be complete. We don't always write in plus energy when we're writing out the equation. We just remember that there's actually a little more energy on the side, on the right side. So where does this energy go? Well, actually it's given to the alpha particle, which has a high kinetic energy. Now we can also write this same reaction, right? Ignore this, we can scratch this out. We can write this reaction in the following way, where instead of using He, we use the alpha sign to represent the alpha particle. So the alpha particle can be written with either notation. The second type we saw was beta decay, which is when a nucleus emits a beta particle and an antineutrino. So imagine we start with hydrogen, and this is an isotope of hydrogen, hydrogen 3, and it has two neutrons and 1 proton. So blue is neutron, blue nu. And here's what happens with beta decay. One of these 2 neutrons is going to turn into a proton. That's beta decay. And when it does, it ejects an electron. We also call this electron a beta particle. Right? It's the same thing. Now, you might be thinking, where's the electron? I don't see it. Well, if we bring our magnifying glass, we'll see the electron. It's not there without we don't see it without a magnifying glass because it's so much smaller than these. So it's massless, right? It's so much smaller than these nucleons. So we need a microscope. Well, you know, we need something a little stronger than a magnifying glass to see it, but you get the idea. So over here now, because we have just changed one of these neutrons into a proton, the proton number has increased to 2 because there's 2 protons. And the mass number, or the nucleon number, is still 3. We still have 3 nucleons here. So we started with hydrogen 3, and through beta decay we wound up with an electron which has 0 mass, 0, plus helium 3, like this. Now, in these equations, now when we write these reactions, we like for the nucleon number on the left to equal the total nucleon number on the right. And look, it does. 3 is what we have on the left, and on the right we have 0 plus 3, which is 3. Likewise, we like the total proton number on the left to equal the total proton number on the right. But on the left we have 1, whereas on the right we have 2. So we write the beta particle, the electron, as having a proton number of -1, just so the math works out. So what we discovered after doing more experiments is that not only is there a beta particle being emitted in this decay, but whenever we have a beta particle emitted, we also lose what we call an antineutrino. So we have to add that in our equation. And we're not really going to study what these are, except to say they were discovered because momentum wasn't being conserved in this. If we didn't have the antineutrino, we found that these two things went in directions that didn't make sense. Momentum wasn't conserved. So we added this in to conserve momentum, and then we found later additional experimental evidence in favor of its existence. And again, if we look at the left side, this hydrogen has more mass than all of these things added up, right? So that means there's more energy on the left than there is on the right. So we really need to add some extra energy for the equation to be true. So where is this extra energy going? Where does it go? It's given to the neutrino and the beta particle as kinetic energy. And that energy is split among these two things in different proportions. Sometimes the beta particle gets all of the energy, sometimes it gets only part. But usually the beta particle is quite high in kinetic energy, so it's moving pretty fast. However, it has a lot less momentum because it's so small. So even though it has the same kinetic energy sometimes as an alpha particle, even if the kinetic energy is the same as an alpha, this beta particle has much less momentum, and it even has less charge. Its charge is only 1 minus, whereas the alpha particle has 2 plus as its charge. So that makes it less reactive on the whole, and less ionizing. Another way to write this is using the beta symbol rather than the electron symbol. So the beta particle can be written as either. And sometimes we even put a minus right here, like I've done in this case. We put a little minus to the top right, and a minus is here as well. Now, the last type was gamma decay, which is where a nucleus emits a gamma photon. And here's an example. We start with carbon-12, and it emits radiation, a gamma photon. And as a result, it loses some of its mass. Right? So we started with carbon-12, and we ended with carbon-12, plus some radiation, some electromagnetic radiation in the form of a gamma photon. We could also write the photon as having some energy h times its frequency. That's true for any photon. And because this gamma photon has such a high energy, gamma is the highest, the frequency will be really high. So we can write it either way. And the thing to notice is the parent nuclide doesn't change. It's carbon-12 in both cases. Now, this type of reaction, or decay, usually follows either an alpha decay or a beta decay. So sometimes an alpha decay will occur, you'll have a little energy left over at the end, and that extra energy will be emitted as a gamma photon. Now, all of these have involved some nuclei emitting some of its nucleons, right? So, in some transmutations, though, we don't lose nucleons, we gain nucleons. They are absorbed. An example we can study, and that we will study, is neutron capture, when a neutron is absorbed by the nucleus. So imagine we have nitrogen, right? And we start out with nitrogen and also a neutron. And we slam that neutron in toward this proton, right? So it hits the proton and knocks the proton out away. We've just lost one of our protons in this nucleus. So now, instead of 7 here, we have 6 protons. But we still have 14 as the nucleon number. And because we've gone from 7 to 6, we've changed elements. This is now carbon. And up here we can add that we've ended up with an extra proton. So we started with nitrogen, and we slammed into it, a neutron, and we ended with carbon and a proton. So this is an example of a nucleon absorbing, a nucleus absorbing some new nucleon. And here's our original reaction. Here's the same reaction. Initially, this is what we have: nitrogen and a neutron. And at the end, we have carbon and a proton. If we compare masses, the initial mass, right, of the nitrogen plus the neutron, that mass of this system is bigger than the final mass of the proton and the carbon. Right, bigger than the final mass. Which means, in fact, the change in mass, the difference, the mass deficit, or the difference between these two, is this many U, right, this many AMU. And if you convert this into energy, we get 0.65 MeV, mega electron volts. Right? So 0.65 mega electron volts, guess where that's given? That's going to be given to the proton. So it's now got some kinetic energy as well. Right? So we can add that to the drawing. So transmutations where a nucleon is absorbed, like what we just saw, those can occur naturally or artificially. In fact, this reaction that we just looked at as an example, it actually occurs in the Earth's atmosphere. So this is an example of natural transmutation. But we can replicate this reaction in a lab setting by slamming together a nitrogen with a neutron at high speeds. That's what particle accelerators do, right? High-speed collisions. So, nuclear fusion. There's a special kind of reaction called nuclear fusion. That's when we have two small nuclei that join to form a bigger nucleus. So let's say we have a small nuclei, a small nucleus, hydrogen, and another small nucleus, a second hydrogen nucleus. If we slam them together at high speeds, right, we can actually form a helium atom with 2 protons and 2 neutrons. And when we do, we also release energy in the process, so there's a mass deficit. And we can write the reaction this way, right? A single hydrogen plus another hydrogen forms, or reacts to form, a helium nucleus plus a gamma photon. And so that's why we showed the masses being reduced, because a gamma is emitted. So it carries away some of the energy of the system, energy is released, and in releasing that energy and carrying it away, it also carries away some of the mass, because mass and energy are equivalent. Now, fusion is when we join 2 smaller nuclei to form a big nucleus. Right? So let's focus in right here at hydrogen, which has, we see on the axis, its binding energy per nucleon is 1 MeV, and helium, which has a binding energy of 7 per nucleon. Right? So there's helium, there's hydrogen, because those are the 2 things we just had in the reaction, in the example we just saw. 2 hydrogens collide, they form a helium. Now, these numbers, 1 MeV and 7 MeV, we're going to use that right now. Here's our reaction. I want to find how much energy does the gamma have. Well, initially, the binding energy per nucleon is 1 MeV for the hydrogen. That's what the graph just showed us, the binding energy curve. So each of these hydrogens has 2 nucleons. So each hydrogen has a total binding energy of 1 per nucleon, 1 MeV per nucleon, times the 2 nucleons, or 2 MeV. So initially we have 2 hydrogen atoms, and each hydrogen atom has a total energy of 2 MeV, which gives us a total binding energy of 4 at the beginning. At the end, over here, right, the binding energy per nucleon is 7 MeV for the hydrogen, and this doesn't have binding energy. So this helium has 7 MeV as its binding energy per nucleon. So because this helium has 4 nucleons, the total binding energy of the helium on the right is the 7 per nucleon times the number of nucleons, which is 4. And that gives 28. So because this helium is the only thing that we have on the right with binding energy, that's the final binding energy, 28. Now, why did I calculate the binding energies of the two sides, right? So far, the way we found the amount of energy released is by finding the mass deficit from the left to the right. So now we're doing something different. There's an equation that says the energy released in a reaction is equal to the final binding energy minus the initial binding energy. And this is a powerful equation. This is a very powerful equation. So it's a new way to find how much energy is released. This is the first time we've seen this way of finding the energy released. In the past, we would have had to find the total mass of the left, the total mass of the right, and we would have had to find the deficit and converted it into an energy using 931.5 mega electron volts per AMU. This is different. So plugging into the equation, the final binding energy is 28, the initial is 4, and that gives us an energy released of 24 MeV, which is actually quite big. So one more time, there it is. Last time we're going to see it. The thing about this fusion reaction is it's very, very difficult to generate. Each hydrogen nucleus has a net positive charge, which means as they approach each other, right, when we collide them together, they repel electrically. So they start here, we throw them together at high speed, and they do this, and then they repel, right? They don't actually collide. To get them to fuse, we have to throw them together at really, really tremendously high speeds. Only once we throw them together at super high speeds do they ever get close enough for the attractive nuclear force to dominate over the electric repulsion. Okay. But if we don't throw them together fast enough, then they'll never get very close, they'll never feel nuclear attraction, and they'll just come together and then go back apart. Okay. So we need super high speeds to get them close enough to be bonded by the nuclear force, which is only acting over short distances. So there's two ways to get them to move close enough, right? There's two ways to get them going fast enough so that they collide and fuse. One, heat them to the temperature of the sun's core, 13 million Kelvin, right? That's not so realistic on Earth. The other is to smash them together in a particle collider, a particle accelerator, right? And that's not super practical if we're trying to generate a lot of energy from this nuclear reaction, this nuclear fusion reaction. So it's really hard to achieve. A more practical approach is something called nuclear fission. And fission is where we split we split a larger nucleus into two smaller nuclei. So let's compare. Fusion, we have two smaller nuclei. They collide and they release energy when they fuse. Fission is the opposite. We start with a larger nucleus and it splits into two smaller nuclei, releasing energy in the process. Right? So you might be wondering, so here's a good example. We start with uranium-236. It splits to form barium-141 and krypton-92. And in the process, it also releases 3 neutrons. And that splitting of this uranium atom generates some energy as a result. Okay. Now you might be wondering, how is it that an atom, some nuclei, can split to release energy, whereas other nuclei combine, they fuse to release energy? Well, the answer to this question is our binding energy curve. Right? So, here's our equation. Remember, here's our equation. The energy released is equal to the final minus the initial. So, if we start with uranium, okay, it has an initial binding energy of something kind of small, right? Something around 7.5, let's say. It can split into barium and krypton, which each have a higher binding energy, putting the final at a greater value than the initial. So if we start over here to the right, when this thing splits into two other atoms, we lose atomic mass, right? Each of the daughters has less mass and has more binding energy per nucleon. Whereas if we start over here, now, in order to increase the binding energy per nucleon, we have to move to the right, we have to increase the mass and fuse together two different nucleons. Right? So, the way we gain energy, right, the way we release energy in a reaction is by moving toward the highest Be per nucleon point, which is iron right here. So if we're to the left of iron, if we're to the left, over here on this side, we release energy by taking two smaller nuclei and combining them together to get a heavier nucleus. Right? Because that puts us farther to the right on the curve and a higher binding energy per nucleon. If we're on the right side, if we're to the right of iron, the way we release energy is by taking a bigger nucleus and splitting it into two slightly smaller nuclei. Because then the atomic mass has decreased and we've increased, right? We've gone up on the y-axis. We've increased the binding energy per nucleon.